So we're going to take all the points that we've got. Let's go ahead and write them down. What are the points we usually work with? -2, 2. Yes. It's -2, +2. -1, +1, 0, 0, 1, 1, 2, 2. Okay. Oh, hello. You're welcome. All right. So the reflection and the vertical compression both involve multiplication, so we can do those at the same time. So reflection takes something that's up and moves it down. That's a y-coordinate change, right? Up, moving it down, that's a y-coordinate change. Vertical compression, I said, is like when you have a hamburger full of stuff and you take it and you smush it so you can fit it in your mouth. That's what a vertical compression is. And it takes something and it makes it wider, but it squishes it down. So it's shorter but wider. You know what I'm saying? Squishes it. So you can, like, you know? Cool. Okay. So what we're going to do is we're going to take the y coordinates and we're going to multiply them by -1/2. Okay? So what is 2 times -1/2? 1. You're close. -1. Good. What is 1 times -1/2? -1/2. What is 0 times -1/2? 0. Okay. And then 1 times -1/2, we already said, is -1/2. And then 2 times -1/2, we already said, is -1. So none of the x-coordinates changed. All of the y-coordinates multiplied by -1/2. So this right here was a multiply. And these are your notes, so if you need to add anything else, you can. If you want to write multiply y by -1/2, you can. Whatever you need to do to make your notes make sense, that's what you should do. Yes? We know it's a compression because it's a 1/2, which is a number that is smaller than 1. Smushed. Yep. So the negative told us it was upside down. The 1/2 told us that it was compressed. Okay, and then left one, does that change the x-coordinate or the y-coordinate? X-coordinate. So we're going to take each of the x-coordinates and we're going to subtract 1. So -2 subtract 1, -1 subtract 1, 0 subtract 1, 1 subtract 1, 2 subtract 1. Now, there is no shift up or shift down, so the y-coordinates are going to stay exactly the same. And that means at this point we are ready to graph. So over the summer, I gave my calculus students a summer assignment, and they had to, in their minds, reach back to Math 3 and do this stuff again. Because in calculus, it is very common for them to have to graph something without a calculator, and so this is the stuff they were trying to remember so they could graph things. So for those of you who think that, like, why are we doing this? It's because later on in math, you don't get to use a calculator, even though you'll get to use it on the EOC. If you continue on in your honors math track and choose to go into some of those upper level classes, you don't have to, but if you choose to, eventually you will not be able to use a calculator. And so it's good to be familiar enough with graphing something without a calculator that you still know how to do it years later. Okay, so I took these points, after we transformed them, I took these points, and those are the points that I graphed. So left 3 down 1, left 2 down 1/2, left 1, down 1/2, and then right 1 down 1. All right, how are your brains? Brains are okay? That's okay. The nice thing is that these transformations, we're doing it right now with absolute value. We're going to do it again this unit with quadratics, which you actually did last year, but we're going to do it again. Then we do it again with square roots, cubes. Then we do it again with logarithmic and exponential. Then we do it again with rational. So this idea, this strategy of multiplying and adding and subtracting, we're going to do it like 7 different times. So if it's kind of confusing now, as long as you ask questions and don't give up on it, there will be a point where it will become the easy thing that you've done a bunch of times. As long as you don't give up on it. Okay, as long as you ask questions and make sense of it, there will be a point where it will make more sense. Okay, so looking at the next one. Now this one, we're going to rewrite the problem. So this time we rewrote the problem. We put a +0 on the end because there was nothing on the end. It was like missing the number there. So this one is missing a number on the inside, so we're going to put a 0 on the inside, because normally there would be a number there. There happens to not be this time. So I'm going to say y is greater than 4, absolute value, x plus 0 minus 5. So anytime I have a number missing, if it confuses me to not have a number there, just go ahead and put a 0, and then you can kind of make sense of things. So does anyone know what the vertex is? 0, -5 is exactly right. I think actually, if I look at the baby animals, there is, okay, it's a giraffe. If you confuse the transformations, so it's very common for students anytime they see a negative to just assume that negative means compression, even though it means reflect. They just see a negative and they're like, oh, that's a compression. That's very common. So if you mix up the transformations, you kill a baby giraffe. So those are the 2 things we're looking out for today, because there actually are some inequalities. So if you shade an inequality wrong, you kill a baby sugar glider. If you mix up one of the transformations, you kill a baby giraffe, okay? So I'm just going to be walking around seeing if you're killing babies today. And if you want to kill babies, that is fine. You can be malicious if you want. We will judge you for it, okay? Notice I said we will, because that's terrible of you. But if you want, that's fine. It's just terrible of you. All right, I'm going to move on. Okay, so we got this. So if you tell me this is a compression of 4, you kill a baby giraffe. That's fine. You can kill a baby giraffe if you want to. I'll just make you mark the tally of shame. We're going to try to avoid killing baby animals because that's the nice thing to do. You know what I'm saying? Okay. So what is the 4? 4 is bigger than 1, so that's a vertical stretch. It makes the graph appear to be very narrow. So it makes it 4 times as tall as it normally would be. So it's very, very, very skinny. All right, so it's a vertical stretch. There's a 0 right here, so there is no left or right. Nothing happening there. What about the 5? Down 5. Okay, so I'm going to write my points. The vertical stretch of 5, that's a multiplying thing. It makes the graph 4 times as tall. 4 times as tall means you're multiplying something. Shifting down 5 means you're adding or subtracting something. So when we do our transformations, we always do multiplying transformations first. We do adding or subtracting transformations second. So when you stretch something vertically, making it 4 times as tall, is that happening to the x-coordinate or the y-coordinate? The y-coordinate. Y-coordinate is up and down. So making it 4 times as tall, so I'm going to take the y-coordinate and I'm going to multiply it by what? 4. So we got -2, 8, -1, 0, 0, 1, 4, 2, 8. Okay. And then we're going to take each of the points and we're going to shift them down 5. So is that an x coordinate change or a y coordinate change? It's a y coordinate change to go down 5. So taking the 8 and going down 5 gives you 3. Taking 4 and going down 5. Okay, 0 going down 5. Okay, and then we already know the last two. It's -1 and 3. Now, when we graph this, we have to be careful because I actually made it an inequality. It's a dotted line. I was tricky about this one. So we gotta make sure that we connect those dots with a dotted line. What point do we typically plug into the inequality to see where to shade? 0, 0. Why do we choose 0, 0? Because we are lazy. It's easy to plug in, and we are lazy. Okay, so 0, 0 is right here. So when you shade for an absolute value graph, you're either going to shade inside or outside. With a line, it was kind of like above or below, left or right. When you're shading a V-shaped graph, it's either inside or outside. Okay, so I'm going to plug in 0, 0. I've got 0 is greater than 4 times the absolute value of 0 minus 5. Somebody tell me, what's the positive version of 0? It was just 0. Okay, so 0. What is 4 times 0? Okay. What is 0 minus 5? Okay. Is it true that 0 is bigger than a negative number? That is true. Okay. So where the 0, 0 was, that was true. So the inside is true, the outside is false. So you shade the inside. No sugar gliders died during this problem. That's good. That's how we like it. Okay, okay. All right. The domain is all of the x values, which are numbers that you input. These are inputs that are defined in the function. That means you can plug a value. This blank is way too long. You can plug a value. That's it. You can plug a value into the function and get an answer. I don't know why I expected you guys to write plug a value and have it take up that much space. Did anyone take up the whole space? No? You did it on purpose? You're like, let me write in my widest font possible. I don't know why I thought it would take up that much space. The range is all the y values, which are outputs, that are defined in the function. So basically, this is the answer that you get after you plug an x value. Okay, are you guys ready? In. The word in was supposed to take up this whole line. I don't know what I was thinking when I made those blanks. It's real good. Okay, so what I did is I gave a couple examples just so we could see what the domain and the range would look like on the examples. Now, the nice thing is the inputs for absolute value are pretty easy. An absolute value, when I put a number into an absolute value equation, all an absolute value equation is saying is take the number and make it positive. Is there any limit to the numbers that I can make positive? Either it's already positive and I say make it positive and you're like, it is. Or it's negative and I say make it positive and you say, okay, I just took the negative sign away and now it's positive. So for 0, you just say it's 0. Okay, so the domain always, for absolute value equations, is going to be negative infinity to positive infinity. Okay, and you can see that on a graph because when you look at it, it has an arrow going to the left and an arrow going to the right, and none of the values in between are skipped. You can see every value is getting used. You guys see that? It goes left, it goes right, nothing, like it's all there, okay? So for the domain on both of these, we're going to do negative infinity to positive infinity, just like this. Now, technically, you guys should have seen that notation a little bit last year in quadratics and Math 2. You haven't done it a lot. In Math 3, like I said, we do like 7 units doing this stuff. So it's okay if we do this first unit and you're a little bit like scared of it, because as we go on, if you keep asking questions, it will get more and more comfortable, okay? That's kind of the goal, is that it's a little bit shaky at first, but then we get better and better at it. Okay, range is where things are a little bit wonky, okay, because the range can actually change depending on the problem. So if you look at this, we can see the arrows are going down. You guys see that? Down arrow, down arrow. So we're going to say this range, it goes down forever, so we're going to say negative infinity. And then the graph stops up here. It does not go any further. And can you guys tell what y value it stops at? 2. So we're going to say the range is from negative infinity to 2. And since it actually is a number that I can put my finger on, I can stick my finger right there and say, that is 2. That's where the graph stops. I put a bracket right there. Okay, so I'm going to say bracket because it stops there. Stops there, that's an actual value on the graph. It's not just getting close to 2, it's actually on 2. Okay? Now this next one, it doesn't go down forever, it stops at a specific value going down. Can anyone tell what the specific value going down is? Negative 7. So negative 7 is the one we're going to put first. And because it's a specific value, we're going to put a bracket around it. And then we have arrows going up. You can't really see the arrow on the left side. It'd be over here. Okay, we have arrows going up forever. And so that's an infinity. Positive infinity because it goes up. So whenever we write domain, we go left to right. Whenever we write range, we go down to up. And if you forget, I made you a poster over there. Do you guys see? Poster? Left, right, down, up. Isn't that fun? So when you put your notes away, it's like you still have them out because there's a poster. Thanks, Miss Rice. You're welcome. Okay. The vertex. We already kind of figured out what a vertex is because we have looked at the vertex as that little point that is like where the V changes directions. It's going down and then it switches and goes up, or it's going up and it switches and goes down. But here's the actual definition of a vertex. A vertex is the point where the graph switches from increasing to decreasing. Or vice versa. We often think of this as the middle of the graph, or we might think of it as the starting point. A lot of people graph the vertex first. Some graphs don't have a vertex, so some graphs don't go down and switch directions and go back up. Some graphs like come down and hit a middle point and then keep going down. So technically they don't fit the definition of a vertex, but they still have like a special point. And so in that case, I like to call it the locator point. I don't know what people technically call that, but in this class, I'm going to call it a locator point. Now, I said that for each unit, we're going to find all these different things. I'm going to give you this set of notes each unit, but we are only filling in the blanks this one time. After this, I copy-pasted this over and over and over again for each unit, and I just switched out the example problems, so you guys will have these definitions every unit, okay? There will be no brain farts in this class. I mean, there might be brain farts, but it won't be on definitions. All right. The vertex and locator point are found in the equation using the h and the k. You guys already knew that. We've done that. And you write it as h comma k. Right. The increasing interval is the x values that make the function. Whenever they say function in math, they're really talking about the y values. That really messes with students. So anytime they say the function, they're really talking about the y values. So the increasing interval is the values that makes the y values go up. This is where the graph slants up to the right. Now here's a lovely typo that got copy-pasted on every single unit. You guys love it? It says the y values, it should say x. Increasing and decreasing is always x values. All right, decreasing interval is the x values that makes the function, aka the y values, go down. So this is where the graph slants down to the right. I made you guys a poster for that too. Look, increasing, decreasing. Isn't that fun? That's what I did this weekend. I took naps and made posters. So, good times. It's like, I think you guys are important. And also sleep. See, there we go. We were all on the same track this weekend. You guys did math homework. I made math posters for you guys to do more math homework. I'm going to stop talking. Okay. So for this one, this is how I teach increasing and decreasing, and you're going to think it's stupid, but it's going to help you remember. So what we do is we go from left to right because we're Americans and that's how we do things. So we're going to put a little stick figure right here. Okay? Everybody put the little stick figure. Did you draw it? None of you guys drew the little stick figure. Okay. He's right here. He's right here. Okay. Now, a left arrow is a negative infinity. So we're going to put a little negative infinity right here. A right arrow is a positive infinity. So we're going to put a positive infinity right there. Okay. Now, if this stick figure started walking, is he walking uphill or downhill? Downhill. So he is decreasing. Oh, okay. And then he hits an x value right here in the middle where he switches from walking downhill to walking uphill. What is the x value, not the y value, what is the x value that makes him switch? It's 0. It's not 1, that's the y value. The x value is 0. Okay, 0 makes him switch, and then he is increasing. Okay, so here is the increasing interval. I'm going to cover it up. The increasing interval is 0, infinity. That's the answer. Wasn't that tricky? It's tricky. You guys aren't excited. Okay, so the answer is 0, infinity, and we only use parentheses because otherwise we kill baby raccoons. You're going to come home from school today, and your parents are going to be like, how was school? And you're going to be like, my math teacher is obsessed with killing baby animals. Well, there we go. All right, the decreasing interval, if I cover this up, what is the decreasing interval? Negative infinity to 0. We say negative infinity to 0, not 0 to negative infinity, because we're Americans and we read left to right. So that's how we know which order to put them in. Negative infinity to 0, because we're Americans. Yes. Say it again. You do not put a bracket because, let me tell you why, hold on. No bracket, because if I cover up everything and I only put the 0, just right there, just that single point, and I ask you, does that single point slant up or down? It doesn't do either. That's why it's a parenthesis. Does that make sense? That was a really good question. All right, let's do the next one. So I got my little stick figure. I have a left arrow, so that's a negative infinity. I have a right arrow, so that's a positive infinity. So when my stick figure starts walking, is he walking uphill or downhill? Uphill, so this is increasing. Okay. What is the x value? The x. What is the x value that makes him switch directions? -5. Okay. All right, so he hits -5, and now what is he doing? Decreasing, going down. Okay, so my answer for increasing is what? Negative infinity to -5. Hold on, I'll answer that question in a second. Okay, I cover this up, and then what's my answer for decreasing? -5, positive infinity. Okay, we never bracket because if I cover up everything except for the -5 and I just leave that little dot, Keld, can you tell me, is that little dot slanting up or slanting down? Look, it's a circle. It's a little circle. Is it slanting up or slanting down? Is it slanting up or slanting down? Is it slanting up or slanting down? Neither. It doesn't make sense, right? A question about a little dot like that doesn't make sense, does it? So we do not put brackets because a bracket includes that number in the answer, and including the -5 does not make sense. Which is why if you put a bracket on one of these answers, you're going to kill a raccoon. It wasn't specifically for this answer, it was for all the answers. Yep. Good question. All right. How do we feel about increasing, decreasing, and stick figures? They're pretty cool? We can handle it? What? They help. I thought you said the stick figure toe. And I was like, what? What about the toe of the stick figure? Okay. Let's move on. Maximum, minimum. Go ahead and put the word local in front. There's something called an absolute maximum and minimum, which they study more so in upper level math classes. We are only going to do local maximums and minimums. So the local maximum or minimum is the location of the highest value of the function. And when I say function, I really mean the y value. So it's the highest y value and the location of the lowest y value. And we're going to write it like a point. And for this unit, it's just the vertex. We're just going to say the vertex again. And we're going to be like, oh, on that problem, the vertex is the highest point. Oh, on that problem, the vertex is the lowest point. So these are going to be pretty easy for us. We just have to say which way they're going. So it says, draw an example of an absolute value function with a maximum of 3, -2. So the vertex has to have a highest point of 3, -2. So should the absolute value function go like this? Should it go like this? Or should it go like this? It should go this way. It should be upside down. Okay, so we're going to draw the point 3, -2. There's 3, -2, and we're just going to make sure it's upside down. That's how we draw a maximum at 3, -2. Okay? Three -2? Maximum? Maximum? 3, -2? No? The next one says draw an absolute value function with a minimum of your choosing. That's right, you have the power. You have the power. I'm going to make mine really narrow because I feel like it. I made mine have a stretch of 2. Okay. All right, x-intercept, y-intercept, that's not new, right? These words are not new to you. The x-intercept is where the graph crosses the x-axis. The y value always equals 0. So the point is always written as x comma 0. The y-intercept is where the graph crosses the y-axis. The x always equals 0, so the point is always written as 0 comma y. So the first example is kind of nice because you can actually tell what the intercepts are just by looking at the picture. Can you guys tell me what the x-intercepts are? Where does it cross the x-axis? Okay, -6 and 2. -6, 0, 2, 0. Okay, what's the y-intercept? Okay. 0, 2. Okay, the next one is going to not be nice because I put a pi in the equation. You guys see that? I was being crazy. Okay. Continuity. Are there? A graph is continuous if you can trace it with your finger without picking up your finger. Can you guys trace this with your finger? Yes? Absolute value functions are always continuous. Most of the functions that we study are continuous. Not all of them, but most of them. All right. End behavior is the one that messes with students the most. You're probably going to have a hard time with it. It describes the arrows. It describes the arrows, okay? So we have 2 different ways we can describe the arrows. We can describe if they're going to the left or if they're going to the right. And we can describe if they're going up or if they're going down. Does that make sense? We can describe if they're going left or right. We can describe if they're going up or if they're going down, okay? So here's what I want you to write. We're going to put negative infinity over here, positive infinity over there, okay? So this is left arrow and right arrow. Left arrow and right arrow. And then we also have positive infinity and negative infinity. And this is an up arrow and this is a down arrow. So every arrow that we describe, it gets 2 descriptions. Is it going left and up? Is it going left and down? Is it going right and up? Is it going right and down? And we call it end behavior because it's the end of the graph. Does that make sense? Okay. So what is this arrow doing? Left and up. Okay. So left is an x value. Up is a y value. Does that make sense? Okay. Because it points left. See how it's pointing to the left? Like it's... Yeah, it's pointing left and it's pointing up. So I'm going to say as x goes, I'm using an arrow, as x goes to negative infinity, that's the left part. See? X. So I'm saying x because I'm saying x is left. So left arrow. This is how I say left arrow in math. See? So I'm saying left. As x goes to negative infinity, y goes to positive infinity. So this is fancy math notation for left arrow pointing up. Left arrow pointing up. And then for the other one, I'm going to say right arrow pointing up. So I'm going to say as x goes to positive infinity, y goes to positive infinity. So left arrow pointing up, right arrow pointing up. I just wrote it in math notation because mathematicians are pretentious and they like to say things specific ways. And this is the specific way they like to say it. Okay. So the left arrow is pointing up. The right arrow is also pointing up. Miss Rice, why can't we say that? Because you were not the mathematician who invented this. I'm sorry. I don't know. Okay, so now we're going to say the left arrow points down as x goes to negative infinity. So this is how we say the left arrow. The left arrow. How do we say points down? We're going to say y negative infinity. The left arrow points down. Okay? And now we're going to say the right arrow points down. As x goes to positive infinity, the right arrow, how do I say points down? Negative infinity. Oh my gosh, you guys are saints for listening that long.